Thank you very much. It's a pleasure to be here and give this talk. I'm giving the talk instead of Danny Katzman, who couldn't come because he's on RICRA hearings this week. And so I'll be talking about the environmental management modeling activities at Los Alamos. So it'll be slightly different from most of the other talks we heard. I mean, I'll be talking about performance assessment, but mostly I'll be talking how this performance assessment and risk analysis can be applied back to guide environmental management. I'm at Los Alamos. I'm PI or task lead for the flow and transport modeling, which is conducted at Los Alamos. But I'm also on the asking task lead for decision support. So practically, I kind of have a strange position talking both as an asking person and as the site application person. I'll give you short kind of overview of the work that was conducted in Los Alamos, and I'll try to emphasize the importance of the groundwater for all the decisions we're making. I'll discuss the contaminant, existing sources and material disposal areas, history of the research, which was groundwater related work that was conducted at Los Alamos, which kind of has three phases, which is kind of initial monitoring, substantial characterization effort, which was conducted from till 2005, and after that we have more decision support or decision-oriented modeling and activities at the site. So also I would like to mention, I mean, I'll be frequently discussing the number of the wells we're drilling, because in Los Alamos, because of the hydrogeology and complexity, some of these wells are very expensive, and in order of $2.5 million. So really the decisions related to characterization are very important. So the site, I mean, most of you might be familiar, but I'll just briefly overview the location of the Los Alamos. This is the Española Basin, which is a kind of part of Rio Grande Rift Zone, complicated geology, multiple faults and fractures. This is a volcano, which is provenance for some of the rocks that we observe at the site. We have other volcanic activities in this area, which also resulted basalt flows in the subsurface, which impact our flow and simulation models. And so this is Rio Grande. This is the caldera of this volcano, which is right above Los Alamos. This is part of the Rocky Mountains, Sangre de Cristo. And we have, I'll be discussing the existing water supply wells and water use of the water in the aquifer, but some of the water supply wells within the LANL site and also in the close vicinity of the LANL site. So really, aquifer, which is in this basin, is important source for water supply in the area. Just some of the complexities. As I said, this is close on the rift zone, and we have multiple volcanic activities which created some of the basalt in the subsurface. And right beneath area G, which is one of the areas, material disposal areas at Los Alamos, we have really very pronounced heterogeneity, and maybe some of the wells even detected dike, which was going vertically through this area, and we have cinder cones, which may be an indication of the other vents which exist in the area. So really very, very complicated stratigraphy and heterogeneity. So overall picture, I mean, this is the kind of the red area that outlined here, which includes Los Alamos. And here I'm just summarizing some of the important sites which exist at Los Alamos, and for some of them I'll be talking here what kind of modeling and research we conducted on them. And so this is again Rio Grande, and this is the general flow direction in the area. We have, as I mentioned, water supply wells. They're shown with these blue stars. And we have areas in which we have surface and also observation of contaminants in the subsurface. And actually the red kind of symbols identify monitoring wells which had observed some of these potential contaminants above background. So one of the area which is important is the area of TA16, which we observe high explosives. There is a release of high explosive on the surface and also in one of the canyon bottoms, and we observe some elevated concentrations in the subsurface. The other one, which is relatively important and frequently discussed, is the chromium in the Sandia-Mortondet Canyon area. We have concentrations of chromium above, substantially above MCLs in the regional aquifer, very close to existing water supply wells and also close to LANL boundary, which is one of our potential points of compliance for off-site migration. So the other important area, which also will be talking, is TA54 area, where it's area G, L, and H, these are material disposal areas. Here, this is, excuse me, some of my figures are outdated. This is June 2009 figure. Actually, one of the wells which is kind of showing that we have tritium above background. Actually, the new data, because we did additional analysis, actually suggests that there is no elevated tritium there. So this is not up to date. So I'll be talking mostly about those three areas: TA54, TA16, high explosives, and the chromium site. Just again to give you a perspective about the amount of regional and intermediate wells that they drilled in Los Alamos. This is a map, and with the red stars, we're showing here only the well, oops, I'm sorry, which are going to be drilled in this FY, and substantial amount of wells drilled close to TA54 area, also related to chromium plume, and also in the area of TA16, the high explosive site. And I'll be talking about this later, but all these wells are cited based on numerical models and other considerations which are used to guide where to put these wells. So this is important aspect of our environmental management modeling activities. So brief summary of why groundwater, what are the complexity of the groundwater at Los Alamos and why it's important. Really, it's key for most of the remedial actions and remedy selection, and we have multiple, multiple zones which are interconnected. We have alluvial groundwater in the canyons, which is associated with streams which predominantly fed by snow melt recharge, so it's not perennial streams. There are perch intermediate groundwater, which is due to infiltration of this water in the subsurface. Typically, we have also perching horizons, which create complexities and not strictly 1D vertical flow through the vadose zone. And we have regional aquifer, which is again highly heterogeneous and with a lot of water supply wells in close vicinity to the sites. And most of the water from these three systems discharge into Rio Grande, and we also have at Rio Grande diversion projects for water supply, so we really need to consider all these aspects. And here kind of summarize the important issues related to why groundwater studies in Los Alamos are complicated, which relate to the thick vadose zone, spatially and temporally variable infiltration rates, which create potentially different flow paths in time and space through the vadose zone, highly heterogeneous aquifer, and water supply wells in close vicinity. From the regulatory point of view, as I mentioned, there is a consent order between Los Alamos and New Mexico Environmental Department, which drives most of the work which is conducted at the moment. The goal is everything should be completed by 2015. Really, it's important, as I said, In the consent order, it's stated that actually concentrations shouldn't exceed in MCLs anyway in the aquifer. And so this is our kind of target in our activities, even though at the moment we have MCLs exceeding, we have concentrations exceeding MCL in the chromium area, and there is no particular action from NMED. I mean, of course, we're doing a lot of studies, but really at the moment, this doesn't require active remedial action. We're still in the characterization phase. So highlights of our communication with the regulators and stakeholders, which is important, is that really initially there was a lot of distrust of the modeling and anything related to application of models. But more or less we kind of gain confidence and working, having regular technical meetings with regulators, stakeholders helped. So we have relatively good acceptance at the moment for application of models in our environmental management. Various modeling activities which are conducted in Los Alamos, I mean, I kind of summarize them on a high level. I mean, they're with different scale and resolution and different dimensionality. We use 1D and 3D models, model abstractions. We use a wide range of processes in our process and also kind of system models. And we use, as I mentioned, complexity in terms of complexity, use system and process models. And we kind of divide the modeling activities in terms of their purpose as a characterization models, which helps mostly with the characterization of the regional aquifer and the properties, and also the one which are really guiding and helping the decision support. And I want to emphasize that really, I mean, the model-based kind of component of the decision support. And the decision support is guided by the performance and the risk at particular site. So, I mean, practically, that's why I'm saying that I'm not talking explicitly for performance assessment and composite analysis, which we're doing. I'm talking mostly about the aspects of the performance and the risk for particular sites, which we identify and use this information to go back and provide some guidance for decision support related to remedy selection or related to additional characterization effort, optimization of modeling networks. In general, we prefer to use process models, but we also use system models in this process. And we try to use efficient model analysis tools and efficient simulation techniques which allow it to use process model even in this framework. One of the important critical aspects of the modeling activities we're doing is, I mean, most of these things were mentioned yesterday and today when people were saying what are the guidance for the ASCIM and what are the particular modeling needs. I will definitely say that really keeping good record of everything related to model development is critical aspect. And in many ways, I'll say that this is a substantial bottleneck. I mean, maybe this is because of my background, or I mean, I feel much more comfortable to let the computer model to run for a month or a week using multi-process machines, and I'm not that much concerned that this might be taking a lot of time. This is really difficult, and we don't have sufficient tools and sufficient methods to really create perfect traceability of everything that we do in the process of conceptual development, justification of various conceptual model assumptions, what assumptions were involved in numerical model development, what are the data sources, references, knowledge which incorporate in the modeling, and also the inputs which we're getting from the stakeholders and regulators. And version control is also part of this, but it's a relatively small part of this. I mean, this is, for me, important aspect. To help this, we try to use as much as possible automated data transfer between databases and models. We strive to improve the computational efficiency through using advanced techniques, both for simulation and model analysis. And we also use scripts intensively for coupling and pre and post processing. Substantial amount of data is collected. I'll not go through this slide. This is kind of listing all the data which was collected, and currently most of the information is available on the web, so you can query it outside of LANL. It's not behind the firewall. In the rest of the talk, I'll talk about examples of modeling work at Los Alamos, characterization. I'll talk about some of the modeling work related to characterization and decision support. And in characterization now, when we talk about characterization, we'd say use the models to test, evaluate, and rank potentially conceptual models, to estimate aquifer properties, to evaluate the nature and extent of the plumes, source identification. These are just examples. Again, decision support, again, I would say is model-based decision support. I mean, when you say decision support, I mean model-based decision support driven by performance and risk. And related, some of the tasks which I'll be discussing is evaluation and optimization of characterization activities, monitoring, network optimization, optimization of remedial options, and again, performance assessment and risk assessment and composite analysis. What we would like to achieve is practically to be part of this process and be able to use the results from this analysis in our evaluation efforts. Just a slide with to show you some of the models that were developed on the site. We have a range of models, numerical models, which go through the whole basin, Espanol basin. We have model coupling with the smaller side scale model, which is just at Los Alamos. This is the same type of scale which is shown here. And this is more or less the model which we use for the chromium site, one of the examples. Very complicated 3D model, much more refined. So again, model coupling between this model and the side scale model or facility scale model. So this is Los Alamos and this is the chromium Morton site. And this is just zoom in of this model to show the meshing or the gridding of the model that we use. But we're not using only numerical models. That's why I put this nasty equation here, just to show you that, we use also analytical methods as well, because it's required to be able to do this analysis quickly as possible, and this is also very useful screening tools. So I'll start with the chromium project, and I'll just first introduce the amount of data that we have and the information that we have about the conceptual model and the data, and after that we'll show you the model that we supplied to the site. So this is the Sandia Canyon, which is where most of the chromium originated. Initially was infiltrated along the canyon, but the infiltration have a complex flow path and practically appears that is observed in the regional aquifer beneath adjacent canyon, which is Morton Dead Canyon. Both of the canyons have some water which drives the infiltration through the subsurface. So in this case, this is one example that practically in the radar zone is difficult to use 1D simulation to characterize the subsurface or the flow and transport to the subsurface. So the kind of this pinkish area is the area which with 2 wells we observe chromium above background. Initially we drilled R22. This is the first well which showed it. The next well was actually identified based on our modeling activities where to place the next well, and really got it on a good spot which we expected. Data for each well in the area, I'm just showing a bunch of data which relates to what are the hydrostratigraphic unit which in this screen is located, what is the permeability and what is the chromium value observed in these wells. So we use all this information to kind of construct our models. Important conceptual model uncertainty is the anisotropy and heterogeneity that exists in the aquifer, which could provide uncertainty in the flow direction, in the transport direction of the contaminants in the regional aquifer. So that's why we have this kind of arc of uncertainty which drives some of our work, because we need to take into account this conceptual model uncertainty. And again, I'll mention that we have water supply wells in close vicinity to this plume, and this is critical. I'll talk more about this later. As a cross section, again, the same area. This is Sandia Canyon. This is more or less the source where originally chromium was released. It infiltrated, it moved along the canyon bottom. Most of the zone of filtration expected to be in this area. It expected to be complicated because of heterogeneity. Here, these are basalts, the rest of sedimentary rocks, this is also basalt. So it's complicated, and really, this is conceptual, but also supported by some of the well data which we have from the side, that we have potentially perching somewhere on the bottom, so within these basalts which divert and impact the groundwater flow. And here is where the chromium observed, but as I mentioned in the previous slide, shifted to the south, potentially due to perching horizons. Numerical model that was developed, I mean, the goal was to incorporate all the existing uncertainties about the conceptual model and the existing data which was used for calibration. And even though we have all these kind of uncertainties, we were able to use this model to provide important information for some of the metrics which are important for us at the moment, both for characterization and also for decision making. On this slide, again, I'm showing here is the Sandia Canyon, here is Morton Dead Canyon, here all the wells which we have in the area, and here is kind of on the bottom is the regional water table and kind of the best estimate of the chromium plume based on the modeling in the area. And this is the general flow direction in the regional aquifer. We used a numerical model to analyze the 3D flow through the Vedus zone. Again, this is Sandia Canyon, this is Morton Dead Canyon. The infiltration along these canyons impact the distribution of vapor water content in the Vedus zone. What these kind of greenish blobs are showing increased saturation. The blue regions are very high saturation, almost fully saturated zone, fully saturated portions of the Vedus zone. And so we have some predominantly vertical fault, but also we have diversion and connection of this infiltration driven movement through the Vedus zone and some migration to the south. This is, for this example, we're showing also some of the advective flow paths which may occur in this case from the Sandia Canyon and how this diversion to the south might be occurring. And you also see the stratigraphy and details that are currently incorporated in the model. Based on all this information from existing data, from modeling of the flow through the Vedus zone and conceptual understanding about the flow in the regional aquifer, we were able to generate multiple plausible plumes which are consistent with the existing information. And I'm here showing only a subset of all these plumes because it becomes very kind of dark. But this is more or less a representative subset. We have potential for really very kind of extreme diversion of the flow to the south, and which kind of provoke and require drilling a new well in this area to constrain this uncertainty. But also we have kind of various different shapes of more west-east plumes and more kind of slanted plumes. And all of this, again, I will emphasize that these predictions, model predictions, are consistent with the data. And we incorporated, I don't remember how many model parameters were considered and certain in this exercise. And we tried in the parameter space for within the uncertainty ranges in the parameter space for all these parameters to find plausible model simulations, then reproduce the existing data. And this was really very computationally intensive approach. I mean, you can consider it to be some kind of Monte Carlo analysis coupled with calibration, even though it's computationally more different. And I'll not have time to discuss. We have a paper on this. If you're interested, I can send you papers. But in a nutshell, is model exploration of the parameter space coupled with calibration. Practically all these plumes were resulting from different plausible contaminant arrival locations on the top of the regional aquifer. Each of these purple dots are showing potential locations of contaminant arrival location in the regional aquifer. So this is more or less the area that we're expecting this contaminant to be arriving in the zone. And now, based on this kind of analysis, and again I'll say this is really very computationally intensive problem, and it's not properly posed and difficult to evaluate, and requires substantial amount of modeling runs. We compute average contaminant concentrations. I mean, this is more or less the expected value based on all these realizations, considering all the uncertainties. And again, I'll emphasize that because of the uncertainty associated with the potential sudden distribution of this plume, we evaluated a series of alternative network monitoring network locations, and we identified this to be the most important. And actually, this well is already drilled, but we still don't have concentration data from this well. But all the indications are that actually is not elevated. So we'll use this new data to further constrain our model. Just briefly to also go back to the issue of juxtaposition or close proximity of the plume to the existing water supply well. So here again, this is R28. This is old figure. We still don't have R42. But these are more or less the wells in the area which I was discussing in the previous slide. And these are all the water supply wells in the vicinity. And what I'm here showing is the water level record which we observe in all these wells. And they show substantial transients, and these are the pumping records that we know for these water supply wells. So it's important for many issues related to predicting fate and transport of contaminants in the regional aquifer to be able to identify and understand better the hydraulic connection between those wells and the pumping wells. And we were able to do this. Again, I'll not go and be able to in details. If you're interested, I can give you papers discussing this kind of analysis, but it's really critical in this case to better understand how the potential pumping is affecting the groundwater flow directions in this area. The other, so this is more or less what I wanted to say for the Chromium project. Now I'll switch gears and talk about TA16. This is the area of high explosives, and this is close to the Pajarito Fault Zone, which is kind of the mountain front. I mean, this is the edge of the caldera, which I was showing on the previous figures, and this fault zone is potentially creating complicated pathways of movement of groundwater from the mountain and kind of propagating into the rest of the aquifer. So we have relatively thick vadose zone in this area. We have relatively high gradients in the regional aquifer due to this proximity to the major recharge area. And we have multiple wells which characterize the flow and transport through the vadose zone. And currently we are kind of in CME phase. We've submitted a corrective measure evaluation report, and the model was applied to perform various issues related to monitoring network optimization, selection of remedies, and general evaluation of the environmental risk. Now I'll talk briefly about TA54 and the AG performance assessment and the composite analysis. You might be familiar with the site, most of you. And so this is located I show in the some of the first figures, relatively close to Rio Grande in this kind of southeastern portion of the lab. And it was operated since '57, radioactive waste, relatively big area. And we developed systems level model which incorporates these multiple processes to characterize the potential pathways of this waste to the environment, to evaluate the environmental risk. And here I'm just showing some of the pathways, radar zone movement, regional aquifer transport, impact of biotic intrusion on the groundwater flow, erosion, surface transport and atmospheric transport. And to facilitate the model, 3D model was applied to extract 1D flow paths which are applied in the systems model. And this is the complex 3D model which was applied to do these abstractions of these 1D flow paths from 8 areas, which is shown here. And all this is coupled in this GoldSim model, and different components are provided by different models. Some of them internal to GoldSim, some of them obtained through lookup tables from other models, or abstraction directly through a model abstraction into the GoldSim. Similar to what some of the previous work were highlighting. We're doing similar analysis on MDIT, which is pretty interesting site. I mean, we're doing now the similar type of approach to what we used in Area G for MDIT, and that's why I'll not repeat this. But MDIT is a former radioactive waste disposal site. It was used from 45 to 74, but what is unique, that's why it's kind of discussed or proposed a potential site for application related to ASCIM, is that really it's the oldest actinide site with very good records of data, significant of RAD inventory, and also there is, I mean, the other issue which is that it's cementatious waste. So we can use or perform some analysis here, or take samples from waste which was deposited almost 50 years ago, and see how these cementatious barriers are performing, and we can learn potentially a lot from these sites. It could be important both for ASCIM and also for cementation barriers. I will talk about general monitoring network evaluations which we're conducting at the site. And here, I mean, this is somewhat similar approach what we discussed earlier. What we're doing, and I apologize for the quality of the figure. I mean, it's always unpredictable how these colors will show up on the projector, and I always try to avoid to use yellow and kind of pale colors, but I failed here, I'm sorry. So again, this is Rio Grande, this is the Los Alamos area, and I'm showing as the dots the existing wells, and this was a relatively old figure. It's not showing the most recent amount of wells, but this is really related to the time which we conducted this analysis. So we have multiple areas that we might expect that contaminants might be reaching the regional aquifer, and these areas are shown with these red polygons. So practically in our analysis, we're assuming that these locations that we might see contaminants reaching the regional aquifer, we consider these areas to be kind of source areas and we put dummy concentrations. We use particle tracking techniques. We release kind of these dummy contaminants in the regional aquifer, and the goal is to be able to optimize our monitoring network so that we have sufficient detection and protection efficiency. we targeted 95% detection efficiency level, which means that we would like from all the plumes, again, this is Monte Carlo framework, uncertainty analysis type of framework. We wanted from each of these sites, the existing monitoring network to be capable to detect 95% of the plausible plumes from each of these locations, and also to be able to detect these plumes before they reach water supply wells or reach the compliance boundary, which is more or less the LANL boundary. So these analyses were performed kind of on for different sites, and we grouped different sites based on their proximity and relationship in terms of sources which produce these potential arrivals of the regional aquifer. And these kind of pale zones define the different areas that we kind of jointly analyzed and look for gaps in our monitoring network. And overall, that's why I put these polygons. There is substantial overlap between different sites, but the goal is really to evaluate overall network, even though we did it on the site-by-site basis. And this was really, again, very intensive work. We're continuing this work. We're adding new sites in this analysis. I mean, typically, again, the analysis for this, it's taking something like a week using huge number of processors. I mean, depends how many processors are available in the computers, but you know, in Los Alamos, we're not that much concerned about computer power. So that's why, again, I'm saying I'm much more concerned about bookkeeping and traceability than computational efficiency. I'm joking. So really, this is very computationally intense, and every single site might take in order of a week or a couple of days to perform the analysis, but we use this analysis to guide our monitoring network locations. And here's kind of map which I was showing earlier, and I'll say that all these kind of red stars in the TA54 area, the really critical aspect of this was evaluating all the uncertainties which we have about the regional aquifer, about various parameters in the regional aquifer, detailed Monte Carlo analysis, which kind of looked into all the plausible migration pathways in the regional aquifer, and this was used to guide the location of these wells. And again, I'll say modeling, it was not the only tool that was used to evaluate these wells, but it was an important part. So here are my conclusions. Really, first, Los Alamos, because of many reasons, is a complicated site for environmental management. There is a series of contaminant sources, potential contaminant sources, and material disposal areas. Thick radius zone, variable infiltration rates, both spatially and temporally. Highly heterogeneous medium in the radius zone, in the regional aquifer. Water supply wells in close vicinity, and we have very active regulators and stakeholders, which are very active on technical level. They're very active on regulatory level. They're really, and we have relatively good communication with them. As I said, groundwater is really key to all this environmental management and remedy selection, and models with different complexity applied for our studies for decision making. Thank you very much.
I have a, I guess, sort of philosophical question is where is your compliance point here? If we have Savannah River, if compliance points to the river, well, it's a gaining stream, and downstream of Savannah River, the concentrations will get lower and lower. Mm-hmm. If we take Los Alamos, if you look at the concentration of conservative ions at Los Alamos, and you go down to El Paso, Texas, Juarez, Mexico, they increase by a factor of 3 to 5. So, and also El Paso and Juarez have about twice the people of the whole state of New Mexico. So why aren't we the stakeholders? your risk assessment calculation take the people down where the people are and where the risk may be into account? Or you just look at the river up in New Mexico and talk to New Mexico regulators? So that's just kind of a question overall. Anyway.
I mean, actually, I didn't show my first slide. Actually, there was. Let me go back. I mean, the moment there is 2 diversion projects from Rio Grande plant, and one of the diversion projects, which is for water supply of Santa Fe, it's right next to, at Rio Grande, right next to Los Alamos. So practically, I mean, in our evaluations, this will be potentially much more important to consider as an environmental impact than most of the residents downstream Rio Grande. But really, I mean, it's...
Well, I mean, the concentrations, concerted ions increased 3 to 5 going down El Paso. And Santa Fe is a little burg. There's not 3 million people in Santa Fe.
Yeah, yeah, yeah. But I agree. I mean,
so,
yeah.
But philosophically, when
philosophically,
you have to lose and burn
yeah.
maybe you need to take the risk assessment further down. Discussion.
I completely agree.
Bruce Crow from the Nevada Test Site. I'm really struck by the similar problems that we're addressing that you are. We have complex geology, complex hydrology, et cetera, and to address those uncertainties, we do pretty much the same things you're doing, where we do multiple simulations and look at the alternative models. But I want to ask you a thorny question that we're really wrestling with, and that is, you're looking at multiple scales of model, and I assume you have a regional groundwater model and you pass off to local scales. And how do you, can you comment on how you handle the uncertainty of like your boundary condition uncertainty and your recharge uncertainty, and how you propagate those from different scales of models?
Yeah, I mean, actually, we work with at Quicklis and Carl Gable.
So you know, yeah.
Yeah. I'll give you most probably the same answer that they give you, that firstly this is a complicated problem. Actually, we have a paper which we explored exactly this problem, propagating uncertainty between basin scale and side scale models. And in this paper, what we did is practically we explored use the basin scale model to evaluate really what kind of uncertainty ranges we observe, for example, for fluxes within boundaries of our side-scale model, and after that, we use these uncertainties in the side-scale model. And again, in our analysis, we kind of did it relatively simple. We focused mostly on the magnitude, total amount of flux. We didn't specifically look in the uncertainties related to spatial heterogeneity of the flux between these boundaries, but this is also a very important issue. So,
same problems.
same problem.
Yeah.
Ian Miller from GoldSim. In the fractured aquifers, is there a possibility that the contaminants are very localized and that it might be harder to characterize a uniform plume? Does that make sense?
Yes, and I mean practically we have in the chromium plume area we have 3 wells currently, intermediate wells, which target identification, for example, of chromium distribution in the intermediate zone, and only one of these wells shows relatively elevated concentrations, but they're not that high that is we need to produce the high concentrations that we observe in the regional because of the mixing and everything. So really it's extremely difficult to characterize this, and actually that's why we kind of going saying maybe it's not important. I mean, this is uncertainty which we have to understand that we cannot reduce. Maybe it's better to look at other ways to address this uncertainty, and the moment approach is to look use the regional data to guide us where might be the important dripping points, important complex flow paths which create the regional aquifer concentrations. So I completely agree. I mean, we'll never be able to characterize the zone. It might be to show it on these pictures and confirm the models that we're creating.